In this video, I'm going to explain just a simple way to do matrix multiplication. So here I have two matrices, matrix A in green and matrix B in blue, and let's say I want to multiply these two matrices together. Now the notation that I've used down here is A with the subscript 3, 2. That means this A, this matrix, has 3 rows, so 1, 2, 3 rows, and then 2 columns, 1, 2 columns, okay? So that's what the 3 and the 2 mean. And B here has 2 rows, 1, 2 rows, and 4 columns, 1, 2, 3, 4. So that's what the B subscript 2, 4 is. Now when you multiply two matrices together, their dimensions, meaning the number of rows and the number of columns they have to obey a certain rule, and that is the inner dimensions. So if I take A 3, 2 and I multiply it by B 2, 4, the inner dimensions are these dimensions, the 2 and the 2. They have to match. So I call them the inner dimensions because if you set these right next to each other, A 3, 2 and B 2, 4, these two dimensions are on the inside, and these are on the outside. So that's why I call them the inner dimensions. So the inner dimensions have to agree. Another way that you could say it is the number of columns of A. So the columns of A has to be equal to the rows of B. Okay, that's our condition. And I like to, when I do matrix multiplication, somebody taught me this cool trick where if you set up the matrices like this on a piece of paper, so that you can draw a box up here. So a box like this. This box has 2 columns and 2 rows, right? We could divide it up like this. So this was the first row right here. So, and here's the second row. If it makes a box like this, when you line up the matrices like this, then you can multiply them together. If you try and line them up like this and you don't get a box in this upper corner, then you can't multiply them together because they don't obey this rule up here. They don't obey this rule. Okay, and it's also convenient because when we multiply two matrices together, the resulting matrix, I'm going to call it C here, how many rows and how many columns is it going to have? Well, its dimensions are going to be the outer dimensions. So it's going to have 3 rows and 4 columns. So it's going to have 3 rows and 4 columns. That's just the conventions, the rule. So we can draw this matrix, the resulting matrix, right down here, and if we just make it so it matches these two matrices dimensions on the sides, then we see exactly how big it's going to be. Now, once we know the size of it, what do we put in here? Well, the component here, the first component, I'm going to call this C11. C11 is just going to be equal to the dot product of the first row of A with the first column of B. So first, sorry about that. What I meant to do is this. let's do this in green so that you can see this. So the first row of A, okay, the dot product of that with the first row, first column of B. Okay, so if I take the dot product, I'm just going to take this number right here, so I'm going to take C11 is going to be equal to 1 times 0, so that's this number right here times this number right here, plus minus 2, this number right here, minus 2 times this number right here, times 0, which is going to be equal to 0. So we could actually go in and put that in. Let's just erase this. And go back here and we could just put this at 0. Oh. 0. Alright, so now if I wanted to get this number right here, I need to take the dot product of the first row of A with the second column of B. So I get 1 times 1, 1 times 1, so I could say this is C, first row, second column component. It's going to be 1 times 1 plus minus 2 times minus 1. So I'm going to get minus 2 times minus 1, which that's going to be equal to 3. So this is equal to 3. So then if I wanted to get this component right here, the C13 component, I have to take the dot product of this first row with this third column. And so I get minus 1 times 1, so 1 times minus 1 plus minus 2 times 0. So that's just going to be minus 1. Alright, now this last component over here is going to be the dot product of this row right here and this column right here. So we get 1 times 2 plus minus 2 times 1, which is just going to be 0. There, we've got the first row of our C matrix. Now we've got to do the other two rows. If we do this, now we're going to take the dot product of this row with the first column here to get this component, and we're going to get 3 times 0 plus 1 times 0 is 0, and then we're going to do this column with, this row with this column right here. We're going to get 1 times 3 minus 1 is 2, and then now we do this row again with this column to get this component, and we get 3 times minus 1 plus 0 times 1 is going to be minus 3. And then this one we're going to get 6 plus 1 is 7. And now this one's going to be 0 again because both of these are 0. And then minus 1 times 1 plus 2 times minus 1 is minus 3. Then 1, and then the very last one is minus 2, 0. Anyways, there's our C matrix. Now if I come down here, it's pretty simple, straightforward how to do this matrix multiplication. I just wanted to illustrate. If I had A and B matrices like this, Now you see that they both have 3 rows and 2 columns. If I put them up here, I draw a rectangle up here, we see that this rectangle isn't a square, so we can't actually multiply these two matrices together unless we transpose this and make this a square, because this right now is 2 by 3. So 1, 2, 3 corresponding to these 3 rows right here and 2 columns. So this is not a square. So if we wanted to multiply these two matrices together, we'd have to transpose one of them. We either have to turn this one on its side or turn this one on its side. So I'll have to rotate it, transpose it, transpose, if we were going to multiply them together. So if I was going to do that, it would look something like this. I could let me just erase this here. And we will write this on its side. Alright, let's see if I can remember this. 1, 2, 0, 1 minus 1, 1. So if we rotate that down, we're going to have something like this. Oh, let's just erase it. This is going to be tricky. Alright, I'll see if I can remember it. It's not very important, really, what they are. But 1 minus 1, 2 minus 1, 1, 0, something like that. But now you see this matrix, at least, now we have a square here. So 2 by 2. So we can multiply these together. We could call this was B. Before it was 3, 2, and now it's 2, 3. So I'm gonna just put a little apostrophe up here to represent that it's transposed, which equals the transpose of B3, 2. And so now it actually has 2 rows and 3 columns. So we could indicate that here, just to be clear. 2, 3. So B transpose has 2 rows and 3 columns. Now we can multiply them together, and if we did that, we'd get a matrix that was 3 by 3. Okay? Now, just want to show you that you can do some cool things if you have vectors. So if I had a matrix that was a column vector, so say I have a matrix A that's like this. It's got 3 components. We'll call it A11, A21, A31. Okay, so this is A, and it is 3 rows and 1 column. That's essentially a vector, right? And then if we had B, that was a row vector. So this is B1, 1, B1, 2, and B1, 3. So B has 1 row, 3 columns. If we did matrix multiplication between these two, we would actually get a 3 by 3 matrix. Alright? So that's cool. We can actually do matrix multiplication with 2 vectors and get a matrix. And this kind of matrix multiplication of 2 vectors is called an outer product. Outer product of two vectors. So, and it results in a matrix. Okay, so this component, first component here, is going to be A11 times B11, and this one's going to be A11 times B12, and then A11 times B13, and then A21 times B11, A21 times B12, A21 times B13, etc. You get the idea. So I've introduced you to the outer product now, and if there's an outer product, there's also an inner product, and the inner product of two vectors is, let's take our two vectors here, but now let's put the row vector first. Okay, so let's have A, B, 1 by 3. Okay, and so now I've got A1. I'm just going to drop the subscripts, the second subscript, because the vector we typically just has 3 components. And then we could have a column vector B. Alright, has B1, B2, B3. And now we see they form a square up here, a 3 by 3 square. It looks like a rectangle, that's just because I drew this shorter than this one by accident. But their matrix product is going to yield just a scalar, which C, this is just going to be one value. We'll just call it C. C, and so C is going to equal the dot product. We call this the scalar product, the dot product, or the inner product. So a bunch of different names. Inner product, or dot product, or scalar product. Scalar product. Okay, and this is equal to A1 B1 plus A2 B2 plus A3 B3. Alright, so now you have an idea of what these things mean: inner product, outer product, matrix product in general, and hopefully it's easy and simple for you to multiply matrices together. We'll see you in the next video.